Hi, everybody. As people are filtering in, we'll give it a couple of minutes. I know the main ISCA program just ended here, and so we'll wait a couple minutes for people to filter over to this Zoom before we get started. But thank you all for joining. Okay, why don't we get started here? So thank you all for joining the Gem5 workshop this year. I know it has not been exactly well planned due to all of the changes that we've had to go through over the past few months. But thank you all for working with us as we do this. I also thank you for inviting me into your homes. I wish we could all be in Valencia together right now. But think on the plus side, every other workshop we've run has not had nearly the participation that within the first 5 minutes we've already gotten here. Already there's over 60 people here on Zoom and also another 20 people or so on YouTube. Which, by the way, if you're having trouble with Zoom, we also have a live stream, which is this exact same thing going over to YouTube, which I think should work as well. Okay, so this is the third Gem5 users workshop. Since Gem5 was released, which was almost exactly 9 years ago, there was a workshop, I think, in 2013 and then 2015, and it's been a few years. But I hope that we're going to start doing these much more often. So yeah, it's been about 5 years since our last community-wide workshop. There was a smaller workshop with the ARM Developer Summit in 2017, if I remember correctly. But since we've done a community-wide one, it's been about 5 years. So I went back and looked at the program from 5 years ago, And surprisingly, not that much has changed. Looking at that program, there's a lot of overlap with what we have now. In our program today, we're going to be learning about the gem5 GPU model, the AMD GPU model, which AMD was also talking about their GPU model 5 years ago. We have talks about tools to use the simulator better, as well as simulator internals. And so, yeah, I think it's really cool that things have changed, but some things have stayed the same. The biggest change is this year we have a lot of talks about heterogeneous systems and how to model different kinds of components. And so I'm looking forward to those. Okay, so we're going to have, today, we're going to have 10 talks from the community. Longer versions of these talks are online on the gem5 YouTube page. I apologize for this terrible URL. It turns out YouTube requires you to have 300 subscribers before you can make your own custom URL. So everyone subscribe. So you can find the longer versions of the talk on YouTube. And then today we're going to have a Q&A for each one of these talks. Tomorrow, I'm really looking forward to tomorrow, where we're going to have a gem5 community town hall. And so in this town hall, I'm going to give a relatively short 10 or 15-minute talk about gem5 20, the newest release of gem5, and then open it up to community discussion. And we'll see how this goes. But the idea is to try to get as much feedback from the community as we can. Again, I'm really excited that this is virtual, because I think this is going to enable so many more people to interact with us. But we'll see how we end up doing the logistics on this virtual thing tomorrow. So importantly, this tomorrow is 2 hours earlier than today. So I'm in Pacific time. We started at 9 a.m. today. So tomorrow we're going to start at 7 a.m. So at least for me, I'm going to have to set my alarm clock a little bit earlier. Okay, so here is our agenda for today. I think on the official agenda, we have 10 minutes for everybody, but we're not going to hold everybody to exactly 10 minutes. We'll just kind of use this as an ordering. But we have a lot of really cool talks, from things that make the simulator easy to use to new models within the simulator and different use cases of the simulator. So let's see, a quick question over here from Shubham. Will the slides be available? I am happy to make my slides available. I will ask all the presenters to send slides as well, and we will put links on the website. One thing that is available right now is, I think every talk has a small blog post to go along with it, which is, a little bit of an informal kind of paper about whatever work they're working on. So thank you for that. And feel free to raise your hand or something if I'm not noticing chat messages. So before we dive in, I just want to briefly talk about how this is going to work. And just so you all know, I'm sure you would be shocked to learn that this is the first time that I'm doing anything like this. So what we're going to be doing is each presenter is going to have a few minutes to remind us of their talk. We've given them the option to have a couple of slides. And then we're going to open it up for Q&A. You can use either the Zoom chat or YouTube. Unfortunately, we don't have ways to vote for questions. So I will just be watching, and hopefully I will catch things as they go by. I will read out these questions to the presenters, and we'll have an interaction. For the presenters, I know a lot of these is more than one author. And so if you have multiple authors on, feel free to have anybody answer questions. Okay, great. So with that, let me jump back to the agenda. First up is Ayaz. And so Ayaz, I think I will try to turn this over to you to present. So let me make sure that you can do that. Okay, Ayaz, you should be able to present now.
Okay, thanks, Jason.
Great, we can see it.
Okay, cool. Uh, Hello, everyone. My name is Ayaz Akram, and in this quick overview, I'll talk about gem5 Art, which is a set of libraries to do organized and reproducible experiments with gem5. So basically, gem5 Art tries to identify the existing structure among different components that are involved in any gem5 experiment. For example, in a full system experiment, there are multiple entities, some of which serve as inputs to the other entities, like gem5 repo is input to gem5 binary. And as a result of an experiment, your results are finally generated. So gem5 Art makes sure that all of these entities are given a unique identity and that they are stored in a database, and thus enables reproducibility. Secondly, gem5 Art also makes sure that the interaction between these components, it takes place in a structured way, thus making the job of a user much easier to conduct complicated experiments. Uh, to give you an idea of the kind of things we can do with gem5 Art, we have used gem5 Art for rigorous testing of gem5. We can quickly talk about the Linux boot tests. So in Linux boot tests, we basically test gem5's status for different Linux kernels, relying on multiple configurations, which encompass 4 different CPU models, 4 different CPU core counts, 5 different Linux kernels, and 3 different memory systems and 2 different boot types. So all of this leads to a complicated setup, but with gem5 Art, it's much easier to organize these setups. And the kind of status plots shown in the slide here can be easily generated. For example, in this figure here, um, we have the working status of 5 different Linux kernels for classic and messy 2-level memory systems for 4 different CPU core counts. So let me point out that these kind of studies were not impossible before gem5 Art, but with gem5 Art, they're much easier to do. And with this, I'm open to any questions that you might have.
Great, thanks, Ayaz. So again, as a quick reminder, use Zoom chat or the YouTube chat if you have any questions. As I turn my video back on. Okay, so Juniel asks, what should I do to use gem5 Art?
So you can actually install gem5 Art directly through a PyPy package, basically. It's and a detailed documentation is also available. Um, I can quickly let me see if that's possible. Uh, yeah, I don't know. Okay, it might take some time to change me the screen, but it's all of the documentation is available. It's an open source project available on GitHub. Um, you can download the code. A detailed documentation is available, and in order to use it, you can directly install it through a PyPy package.
Okay, so Vipin asks, does it also support syscall emulation mode?
Yeah, so fundamentally, anything you can do with gem5, you can do it using gem5 Art. So yes. And we actually have an example tutorial to do some system emulation mode experiments with gem5 as well in our documentation.
Okay, we have another question. Will gem5 Art include benchmark inputs as well as simulator inputs?
Will I'm not sure if I'm understanding the question correctly, but if it's about will gem5 Art actually make sure that the inputs to the benchmark are also part of the overall setup, then yes. Um, if you are asking if we provide the inputs to benchmarks, um, then that really depends. If it's available open as an open source thing, then yes.
Yeah, so they say that, yes, that was it.
Okay.
Yeah. Cool, great. Okay, so while other people are thinking about questions, I have a quick question. Would you say gem5 Art is making running gem5 experiments automatic, or do you think it's more of just a tool for documentation of how your experiment was run?
So obviously, documentation is one of the big components. It's documenting everything of whatever we're running. But at the same time, it's automating some of the stuff as well. Well, probably that was not our main objective. The main objective was to make sure that we enable reproducibility through documenting everything. But it does automate some of the complicated things.
Okay. Let's see, people still seem to be thinking about questions. Okay, here's one from Matt Sinclair. Could gem5 art eventually be used, similar to work in other communities, to verify the reproducibility of submitted papers? Great question, Matt.
Yes, that's a good question. So we are not actually fundamentally using gem5 art to verify reproducibility, though it's very easy to do once you have a setup to make sure that it has all the things there if you want to test that a thing is reproducible. And yes, I think it should be not very hard to port it to other tools, assuming that a lot of the components that gem5 art interacts with, which are mainly needed for example, to enable reproducibility, are external components like a database and other tools to create disk images, for example. So yes, I think fundamentally it shouldn't be very hard to port it to other tools.
Yeah, so Adarsh also asks a similar question. And then Matt follows up again with, so Adarsh asks, is this something we can use to standardize artifact evaluation, which I think is kind of what Matt was getting at as well. And then Matt wants to follow up with, what would be needed to progress your tool from the current state to something that we could use for artifact evaluation and reproducibility?
Technically, we have tried to make sure that it's modular in a sense that finally we do all of this process of basically creating artifacts and everything in scripts where there's a certain part which is responsible for running something on a tool or on a simulator. So that part is what's going to be changed if you want to use a different tool, for example. So whatever part of gem5 art corresponds to that. So for example, mainly your run library would need to be updated, but probably artifacts library is not going to need a lot of changes. So it might be hard to exactly pinpoint things, but based on my experience, I think it's not going to be a very big effort.
Great. Yeah, and I'll just follow up on that too, since I'm also part of this work. So I think that gem5 art is a step in the right direction for reproducibility. It does a really good job of documenting what you need to be able to rerun the experiment. And so hopefully you can take that documentation and then be able to reproduce the experiment. To get it to the point where we could really use it in like the artifact evaluations that a lot of conferences are going to now, it's a lot of software engineering effort that would have to go into it. I think the effort by I think Grigori with the he has an artifact evaluation framework. It is a good example, and he's spent many years trying to get that working, and it would take a similar kind of effort here. I hope that we can kind of integrate it into the efforts that he's been making as well. Okay, great. Thank you very much, Ayaz. That was a good Q&A. So now let's see, the next one up is Wendy. So Wendy.
All right, let me see if I can share my screen.
Great, it looks good from here.
Okay, perfect. All right, so, and can everyone hear me?
Certainly can.
Okay, perfect. So I'm going to talk about some changes that were made to the gem5 controller. And so there's two sets of changes. The first set was just adding some new DRM features that were specific for LPDDR5. So we also added some LPDDR5 configurations. So this includes some new timing parameters, but really the crux of the changes were to support new features, multi-cycle commands specific to LPDDR5. That means there's a 2-cycle activate and potentially a 2-cycle read or write burst. And then we also added a check for command bandwidth. Traditionally, the DRM controller assumes unlimited command bandwidth, which traditionally was an okay assumption, but we're starting to see some corner cases or catastrophic worst cases where that might not be valid anymore. So we added a command bandwidth check, which just utilizes a rolling window, so trying not to be too complex, and we certainly don't want to make this a cycle accurate model. But we use that to verify that we don't issue more commands than can be accepted within that window. And then the last change was incorporating burst interleaving. So as memory technologies are moving forward, we're increasing data rates. And the array frequencies are not really getting any faster. The memory technologies themselves are doing tricks where they're using interleaving within or across burst in order to maintain bus utilization. So we added support for that within gem5. And then the second set of changes we did were a little higher level. So we wanted to take what we have today as the DRAM controller and kind of break it apart into its pieces to enable us to build, building blocks that we could use in the future and add new or support for new interfaces. So we took the DRAM controller and broke it into a generic memory controller, which has the same features and functionalities that we've always had. So the interface to the system, the queuing, the command schedulers, but we just took out the DRAM specifics and made it its own object, a DRAM interface object. And along with that, we created an initial NVM interface that we used to test things out and create topologies with NVM and DRAM hooked up in various ways. So with that, I will open it up to questions and see if there's any other additional inputs I can provide.
Great, thank you, Wendy. As we're waiting for questions to pop up, I guess I can start. So especially with this new refactoring of the DRM controller, it kind of looks like you're splitting it up, kind of like actual DRAM controllers are, where you have the DRAM controller and then a command processor. Is this a reasonable way to think about where the split is between the DRAM interface and the controller?
It is a reasonable way to look at it. The DRAM controller itself will manage things that are media and specific. So it's basically ensuring that we don't have contention on the data bus. And so it manages the read and write traffic to the data bus and scheduling of those commands. But everything that's media specific, so from a DRAM perspective, the activates, the precharges, the refreshes, all those commands that happen to prep up the memory in order to handle the read write traffic, those would be handled with the DRAM interface.
Gotcha. Okay, Adarsh has a question here. So a slightly orthogonal question. Does the memory control interface allow ECC DRAM to be attached?
There's nothing that stops ECC DRAM from being attached. There's nothing within the controller right now that actually incorporates, I guess, the extra metadata that would be ECC, but essentially all that would be is additional metadata. And I'm assuming they're talking about ECC from a DIM perspective. Is that correct? Did I assume that an ECC DIM?
Yes.
Okay. Okay. So, there's nothing to say that we couldn't have a memory that had ECC on it attached from a gem5 perspective, but we don't track, I guess to answer the question more broadly, we don't track that extra metadata through the controller and do the ECC checks and validation. So that's something that would have to be added if that was something that would be desired.
Seems like an interesting thing to add. I hadn't thought about that one in the DRAM controller.
Yeah, there's no, other than that, there's no, from a memory perspective, it's just sent in line with the data. So there's no additional hooks that are needed. But if you want to add the checks and start potentially introducing errors and start understanding how errors manifest themselves, that would have to be added.
Yeah. All right. So Puya asks, in your presentation, you mentioned adding a variable response time for commands in the future, but keeping utilization of the data bus for, let's see. So you mentioned a variable response times, but trying to keep the utilization on the data bus deterministic for non-volatile memories. Could you elaborate on that, please?
Sure. So what I mean by that is from a command perspective, and let's take reads because it's probably easiest to demonstrate with a read. If you have a read command, you can issue that command and the delay in which it's serviced could be longer than typically happens with DRM, or it could potentially even be non-deterministic if you start looking at some of these new medias. So instead of actually transmitting the data back when that read finishes, instead we'll transmit back what we mimic in gem5 as a response saying my data is ready. And essentially that's just an event that's triggered within gem5. At that point in time, the controller can then issue the read or write burst and it will do that deterministically. So we've kind of separated it out, the non-deterministic portion, and handled that with events that are triggered back with additional feedback. And then the deterministic part is managed when we know that the data will be ready and the data is there.
Great. So it looks like I missed a question from Polidoros, which was, for now, I think there's a limitation of one channel per directory in Ruby. Therefore, one channel per memory controller. Will this change in the near future?
Well, first of all, just that, so these changes were more for the classic memory model, not for Ruby. I actually am not an expert on Ruby, so I will probably have to defer that to someone else who could better answer that. To my knowledge, it's not there, but again, I need to defer to somebody else who's has more expertise in Ruby.
So a quick answer to that is so Ruby talks to, the output of Ruby is just a port, so you could potentially put a crossbar there and actually have a single directory talking to multiple memory controllers if you wanted to. Okay, so then let's see, a question from YouTube this time. How much of this controller is configurable for research purposes, and are the service queue latencies monitored?
So from a controller perspective, there's a lot of aspects that are configurable. We can certainly add more features if we need more configuration options. So looking at just the controller, we configure the queue depths, so read and write queue depths. We also have configuration options that manage the bus turnaround when we actually go switch from reads to writes and vice versa. So all of that is definitely configurable within gem5. And then from a DRAM perspective, or now we have an NVM interface perspective, we model the different parameters that are specific to that media. So different delays, page policies, address ordering, and so on. And can you repeat the second part of that question?
Yeah, are the service queue latencies monitored?
So there, from a latency perspective, what's monitored, I mean, I'm not sure I quite understand the question, so let me give an answer and see if I hit it. So we do have, from configuration option perspective, we have what's called front and back end latencies, which are kind of mimicking the latency to get into the controller and the latency to get out of the PHY. And then as far as modeling the behavior, what happens within the controller, there are statistics that are reported that show you the latency of commands as they transition through the controller, and histograms that show you the average latencies that are incurred.
Great. Okay, so one more question from Zoom here. So regarding non-volatile memories, will other aspect of non-volatile memory usage be available? For instance, allocating pages to a certain memory type, persistence models, etc.
So that's some of the future work that I think I listed or discussed in the video. Right now, it's not currently done. The way we've defined The way we've defined the two interfaces is you define a specific range. So that range is just a chunk of memory. How we actually allocate what pages go to what ranges is something that's beyond these changes, but yes, could be incorporated in the future as we move forward and start kind of playing with these models a little bit more and diving into them and seeing what they can do.
Great. Okay, one last question, also from YouTube. Is heterogeneous address space configurable with the new classic memory controller? Can we have channels of different sizes?
Oh, that's a good question. Right now, I mean, right now it's just essentially kind of a crossbar that kind of, we basically go through and loop through the different address ranges and use our interleaving maps to kind of set up how these ranges are defined. I'd envision you could create some configuration scripts that could apply different methods, but the way the memory right now is organized across the different channels is essentially looking at the ranges that we've defined and then kind of interleaving across those channels. But that could change in the future, but that's how it's done today.
Great, thanks. Yeah, and I'll just quickly add on to that. I also had a very similar question. And I think maybe this is something we want to punt and talk about tomorrow during the town hall, which is, do we want to kind of revamp the way address ranges work so they can be a little bit more flexible?
Right. Yeah, that'd be a great topic.
Okay, so I'll take a note of that down to try to bring that up again tomorrow when we have the town hall. Okay, great. Thank you so much, Wendy. And thank you for both of those presentations.
You're welcome.
Okay, so now let's see, where are we? So Garnet, a detailed simulator for diverse interconnects, Shrinkot. So let me turn this over to you.
Thanks, Jason. Let me just share my slides.
Great, we can see it and we can hear you.
Great. Thanks for attending, everyone. I'm gonna talk about Heterogeneous. It's an upgrade to what the network simulator that we have in gem5 currently, which is called Garnet. Heterogeneous improves upon that by adding a lot of components and features that allow us to simulate a much diverse interconnect system, so that we can simulate and evaluate modern systems better. Um, uh, I'll give you an example of 2.5D architectures here, which have a lot of heterogeneity inherent to them. Take the example of such an architecture that I'm showing on the slide. You have a lot of heterogeneity that comes to the interconnect in the form of multiple clock domains, such that you have a different clock domain for the interposer and the chiplet, and the links could be of different flit sizes that are supported by them. You need clock domain crossings and serializer, deserializer units that are needed to evaluate these such architectures accurately. This was not possible in traditional simulation infrastructures that used to support interconnects. They restricted the configuration space, and they usually assumed a homogeneous interconnect system, and that resulted in a lot of inaccurate modeling and potentially led to a lot of suboptimal designs. And that's where Heterogeneous comes into picture. We add a lot of support for heterogeneity within the interconnect, like clock domain crossings, serializer, deserializer units, so much heterogeneity going on within the interconnect. So that's where Heterogeneous comes into picture, and we were able to use this tool to build new and better topologies as well, that I'll show you, that you can read in our upcoming DAC paper. So one of the main things about this is we added these two units called the CDC and SERDIS units. They support clock domain crossing and deserializing support, which you can easily use and implement in your designs. And all of this can be done just by configuring the right topology from the topology file that we use in gem5. And this is supported for both system call emulation and full system evaluations. And Garnet also has a standalone simulation infrastructure where you introduce synthetic traffic into any network that you create. So there's support for that as well. So basically, Heterogeneous allows you to simulate all these heterogeneous architectures. It's not restricted to just 2.5D. It was just an example that I took for my presentation. You could explore a lot of things. So with that, I'm open to questions.
Great, thank you, Shrinkot. Just by the way, you dropped out there for about 10 seconds, but I think we got most of it. So.
Oh, great, thank you.
Okay, so while people are thinking about their questions, I will start. So my first question is going to be, you say Heterogarnet will be released as Garnet 3.0 in the gem5 repository. When? When can we expect to see this?
We are in the process of getting our code reviewed and pushing the code to the mainline repository. It would soon be available, and by soon I mean within a couple of weeks. It would be available in the mainline gem5 repository and possibly future versions of official gem5 releases. So you would be able to use the code base pretty soon.
Okay, sounds great. Okay, so Puya has a couple of quick questions. We'll start with one. Assuming we have two different clock domains, both with the same frequency, do we still need clock domain crossings?
Well, technically, you would not unless they are operating in DVFS modes. So if you have two clock domains, both are enabled with DVFS, then you would want a clock domain crossing because, well, in runtime they could be possibly operating at different frequencies. But if you have static clock domains and they're running at the same frequency, then you would not need a CDC, but Garnet would not stop you from adding a clock domain crossing there uh, to make sure that you evaluate the right conditions and whatever latency is included in the whatever latency is experienced by the clock domain crossing is included in your simulation. So nothing stopping you. It's not necessary unless you're operating those clock domains in a DVFS enabled environment.
Great, thank you. So let's see. Sorry, things are moving. Puyo also asked, do you have any ideas about the performance overhead of Garnet 3.0? I don't know, maybe compared to both Garnet 2 as well as the sample network model?
So in general, Garnet does have a simulation performance impact compared to simple network because we add a lot of detailed router architecture. We are in the process of improving that. And on top of that, Heterogeneous adds some performance impact if and only if you use serializer, deserializer units and CDC units. But that performance overhead, when we measured it, was about 2 to 3% compared to Garnet when running Garnet synthetic traffic. So it's not a lot compared to Garnet, but there's definitely a difference between simple network and Garnet right now, and we are in the process of improving that as well.
Great, thank you. So we'll jump over to YouTube. Rashida asks, since we can set the latency of a router, is the router pipelined or multi-cycle?
The router is pipelined. The initial version of Garnet 1.0, did not have a pipelined router architecture, but Garnet 2.0, which was introduced in 2016, has a detailed router pipeline. It has all the stages that are traditionally there in a router architecture, like input buffer read, VC allocation, switch allocation, crossbar. So there are a lot of there are all the pipeline stages, but you can set the overall latency of the router. So basically, the way it's done is that irrespective of the latency that you set, all these pipelines will be executed. It's just that the total amount of latency that the router experiences is the latency that you provide from your configuration file.
Gotcha. Let's see, Rashiba also asked, is the router configurable to house different flit sizes? For instance, north supporting 32 bits and east supporting 128, sorry, 32 bytes and east supporting 128 bytes.
Right now with Heterogeneous, it does not allow that, because we would want all we technically we want all the flits to go from any direction to every direction. So we do not support that, but there is a way to do that, and that is to have two different routers to basically split that router into two parts, one which supports east and north, or whatever, one kind of a flit size, and the other router supports the other kind of flits, and then you just connect them with another link which supports a flit size that is that and then you include a serializer, deserializer unit between them to allow the synchronization to take place. So it's possible with a tweak. We do not allow a single router to have multiple inputs with different sizes. So because we want all-to-all connection within the router.
Great. So let's see. Matt Sinclair asks, he says, this was an amazing piece of work, but how extensible is it? Will we need to do another heroic effort to design Garnet 4.0 in 5 years? Or have we thought about ways to make this easier to extend as we get new kinds of networks?
When we designed this, we tried to include a lot of future architectures and future technologies that are coming up in interconnect, like on-package interconnects and even optical interconnects. I know a project which is using this for wireless knock modeling. So there is we Heterogeneous supports a lot of future architectures. So hopefully we don't need to modify this a lot to support future architecture, at least in the next few years. But even if we have had to, we made sure that everything that we changed was under the hood, and all the things that you need to do the configuration right now is through the topology file. A user need not have to go change anything in C++. The user can possibly change everything from the Python file itself. So yeah, hopefully Heterogeneous will help us in future architectures as well. Let's see.
Okay, so we're going to try
Thanks,
to get
Matt.
through 2 more questions here. So can Heterogeneous support VCT and wormhole flow controls?
Yes, for wormhole flow control, we do support that. You just need to set the right routing policy and flit policy in the configuration. I think there are some examples available in Tushar Krishna's website. I could point you to that after after this presentation.
Great. And then what kind of topologies will be supported provided at the release? In 2.5D systems evaluated these days, it seems like there's a mix ranging from mesh networks to topologies in your lab have been evaluating. Will the front end be extensible as previous iterations of Garnet?
If I'm right about the question, they're asking if we would give them some example topologies like mesh or something like that for 2.5D architectures. If that's the question, right now in the examples file we have mesh and a crossbar and some of the simple topologies. We don't have any examples for 2.5D architecture, but I think we could include one in the release. That's a great suggestion, and I'll follow up on that.
Cool, great. Okay, we'll do one last one real fast because we only have one other. Oh no, we have two others. Since we have two others, I think I'm going to cut it off then, since we're starting to go a little bit over here. I don't want to get too far behind. Okay, so for those two, Shrinkat can take it offline and respond in chat if you can see that, Shrinkat. So thank you very much.
Yep, thanks. I'll answer them in the chat. Thank you. Thanks, everyone.
Okay, so next we have Francis talking about heterogeneous systems modeling with adaptive traffic profiles.
Right, can you hear me?
We can hear you.
Oh gosh, okay, unmuting, switch where my sound is coming from. Here we go, okay,
So we can hear you fine.
cool. Okay, let's, no, sorry, we're working out screen sharing, I've not had to do this before. Okay, can you see my, okay, share, right, there we go. And that was not the intention. Bear with me, sorry. There, can you see presentation?
We can.
Yay, excellent. Okay, so I will get on with it. So the background of all this was the range of applications needing high performance systems and strong real-time requirements are kind of increasing year on year. And systems that aim to provide that are complex, lots of different elements interacting. So the design task of them is correspondingly more difficult and comes with higher risks. So there's a need for a range of tools to model these. So ARM has released the AMBER Adaptive Traffic Profiles framework. It's as a specification and more recently as an open source reference implementation. ATP is a traffic generator. It's an easily configurable way of injecting data into a simulated system, such as gem5, or it can be run as a standalone simulation. So the profiles can respond dynamically to the behavior of the system that they're in. They can model a complicated device, such as a GPU, solely in terms of its sending and receiving data, while limiting the need of kind of costly simulation. So it's a good way of speeding up such things. As a demonstration of a possible use case, so we present the use in combination with gem5 and also comparing with a network calculus approach to model the effect of contention, write contention on the DRAM memory controller. So the main experiment was to compute the worst case delay experienced by a read and miss that finds a set of other read misses in the queue when it arrives at the memory controller. There are some baseline assumptions being there's a limit to the arrival rate of the write requests arriving there and a limit to the number of read hits that are able to overtake the read in question. Realized I'm missing something else. It's the algorithm that the controller is using in this case is first ready, first come, first served. So read misses are served first come, first served, while read hits are able to overtake them, hence the first ready part. So two methods are laid out here. There's on the left, there are ATP profiles providing the input to a gem5 DRM controller on the left, and on the right, there's a diagram of a finite state machine modeling the same controller. So each state is the represents, for example, serving a read hit, and then each arc is transitioning from state to state with an associated time cost. So the worst case delay is the path that is, goes to. This is moving on when I'm not telling it to. sorry, so it's goes through a read-miss state, say n times, and then that is the longest valid path that it does that. In terms of results, there are two kind of main conclusions that you can that jump out. First, the network calculus approach shows that there's quite a strong correlation, but it does show much longer delays in general than the one from ATP and gem5 when the write bit, and particularly when the write intention is high. The other is the worst case delay is significantly worse in the LPDDR4 memory type than in the other two types that we tested. And the main reason for that was the packets are half the size, so the write rate in bits gets converted to a request rate of double for the LPDDR4 than for the other two memory types. I think that's me done. So questions?
Great, thank you. So let's see, as people are thinking about things, I have a quick question. So how does the this new traffic generator compare to the embedded gem5 traffic generator, which also kind of allows for state machines and you know, some level of configurability?
I know Mateo's on this call. Can I, is it,
yeah,
am I able to palm that question off?
Yeah, I'll take this. Thanks, Francis. Can you hear me fine?
Yes.
Yes.
Cool. Okay, so I'm Mateo, work with Francis in the same team and the ATP implementation architect. So what we thought about when we released ATP was to design a tool that works across many technologies, not just gem5. So I would say that's one thing, one plus. So of course we've released the gem5 integration, but the tool itself is independent from gem5 and can be plugged into different technologies, not just simulators, but also emulators or even hardware devices. And the other thing is that gem5 is based on the concept of ATP FIFO, which is like the basic harmonics in signal theory. So the theory behind ATP is that you can compose those things together to create any specific waveform you want, where a waveform will be representative of, you know, the various phases and you know, peaks and valleys and high bandwidth phases, low bandwidth phases, and so on, that a real application will experience when executed on a device. As an example, I can mention a GPU rendering a frame. If you ever seen a memory trace profile of that, it looks a lot irregular than other things, for instance, mem copies. And the way you would implement that with ATP is just a composition of basic effects that you get out of composing FIFOs in series and in parallel. There's other things that ATP does. So it gives you for free the information that the device is suffering if it's not receiving the expected service that the memory system or the rest of the system that is connected to is providing. So and that is achieved by the FIFO tracking mechanism, which will tell you if it's underrunning or overrunning. And that means that a specific ATP FIFO wasn't capable of delivering the configured rate, which is shown here in the slide. You know, it says 1 GB a second. So it's a tool that's also designed to give you dynamic information about the performances of the system it's injecting into. So it's got a lot of nice features, and it's designed as a kind of a Lego box. So you'll get a few pieces in there, which are namely the FIFOs, delay blocks, an event mechanism that allows you to chain them together, and we also provided a few example profiles in the GitHub release. So hopefully people will use it to design their own profiles, and as I said, plug them into many different systems. There's a bunch of commercial partners who are also integrating this into their tools.
Gotcha.
Sorry for the lengthy answer, but
no, I think that makes sense. So we have a question from Givino, which says, is the ATP available in the last gem5 release, so in gem520?
Yeah, good point. So ATP comes, it's available now, open source. It's available as an extra package. So essentially what you need to do is you download gem5, you then download ATP from the ARM GitHub. You just compile them together by passing the extra flag to sconce. That compiles gem5 together with ATP. You get a new device, which is called profile gen. That is basically a memory object that you can then plug into your scenarios in gem5, and it will inject traffic into gem5. So the GitHub release already includes a test scenario where essentially you get a gem5 device of type profile gen connected through a simple crossbar to a configurable number of DRM controllers. Of course, you can come up with much more complicated scenarios. And because it's an extra package, it's not directly hosted on gem5.org, but it's hosted on the ARM GitHub. So just Google, ARM ATP, you should be able to find it. Or I can share the GitHub link.
Is there any plan for integrating it into gem5, or are you planning on keeping it as an extra?
We've had some discussions internally. It's just that you would have to then maintain 2 copies of it. So I don't know. I mean, I'm not against it, but it's available with BSD clear on our GitHub, so it's freely usable, and I don't think there's any issues in terms of license. I mean, we can evaluate that. I don't see any problems with it. It's just that it will have to stay also on the ARM GitHub because, as I said, it's not purely just a gem5 technology, so we need to release it also without gem5 essentially.
Yeah, that makes sense. Hopefully with the gem5 releases, it'll be a little bit easier for you to have this extra sitting off to the side and keep track of what's going on with gem5. Okay, so one more quick question, and then we'll move on to the next speaker, which is, can I use ATP plus gem5 on the trace of reads and writes for a program compiled on Linux?
Yeah, okay. So that is similar to what we've done internally in ARM. What you would have to do at the moment is to obtain your traces in any way, which includes, tracing applications under Linux, and then analyze them. And we do have a little Python folder in the ATP release, which provides you with 2 tools that are able to analyze traces. Written in a specific format, of course. So if your trace is in a different format, you might have to translate that. So this tool visualizes the shape and form of the signal that you traced. And then it's up to, at the moment, it's up to the engineer ability to reproduce that form into ATP. There's some guidance in the documentation about how to do that, and we can provide further insight. In the future, we might even be releasing our own profiles. I'm not excluding that, but yes, it's all possible. It involves humans at the moment.
Great, thank you.
I noticed a comment that says, "Give us the link." I suppose that's the GitHub, right?
Yeah, I think that would be great if you could do that.
Yeah, I'll copy that on the chat. It's not a problem. There you go.
Okay, great, thank you.
Cheers.
Okay. So let me switch back. Okay, so let's see. We're running a few minutes behind. We will. I'll try to make sure that we don't get too far behind here. So the next talk is enabling multi-GPU support in gem5 by Bobby.
Hello, everyone. Can you hear me?
Yes.
Okay. Let me share my screen.
Great, we can see it.
Okay. So yeah, hello everyone. My name is Bobby Yogarama, and my work is enabling multi-GPU support in gem5. So as GPU become more popular and the size of the applications running on GPU increased, people have started to use multi-GPU system. However, current GPU simulator, such as gem5 and GPU sims, it only simulates a single GPU, which makes it difficult if we want to study issue arising in multi-GPU systems, such as task scheduling and resource allocations. And therefore, in this works, we will extend multi-GPU support in gem5. So we make 3 major changes to gem5, and in our video presentations, you can check it. We discuss in more details about these 3 changes. The first changes that we make is to replicate the GPU hardware components, because obviously we want to simulate multiple GPUs and also assigns each of these components with sort of a different GPU ID to make it distinguishable. The second changes that we make is to enable make modifications to the emulated driver in gem5, because previously it's only managed a single GPU, but now we'll have to make sure that it will be able to manage multiple GPUs. For examples, the emulated driver will have to create the queue and send the kernels to the correct GPU as specified by the user, as well as maintaining the mapping between each queue and the GPU. Other than that, the driver also have to make sure that we map the doorbell to the correct doorbell region for each GPU. And the third and the final changes is the coherence protocol in gem5, which previously only support write-through for its GPU L1 and L2 cache. And to better model what real GPU does, and to reduce pressure to the memory as well, we decided to enable write-back supports into the GPU L2 cache in gem5. So to do this, we pass flush instruction at the end of every kernel to the L2 to flush all of its written lines to make sure that the up-to-date data is visible to the other cores at the end of every kernel. And after that, we run some experiments. We run various benchmark on various number of GPUs, and our experiment shows that the execution time decrease as we increase the total number of GPU. So yeah, that's all. Thank you. Any question?
Great, thank you. So Puya asks a naive question.
Okay.
This is still APU in SE mode, right?
Yes, this is still APU in syscall emulation mode. That's true.
Okay, so we have another question, which is, what kind of networks are supported for multi-GPU?
I'm not that familiar about networks, but in this works, we support APU, which is unified memory. And the model that we use is a single driver multi-GPU node model. So in this case, we use a single driver and then we replicate the whole GPU node.
Okay, so let's see. Brad Beckman asks, have you considered adding support to the GPU protocol tester to test multi-GPU configurations?
I haven't considered that. Yeah, so maybe that could be our plan and as our future works. But right now we haven't done that. But yeah, I will consider that for sure.
All right, so kind of going back to the network supporting on multi-GPU, I had a similar question. So when I think about multi-GPU, I either think about multiple GPUs on the PCIe bus or connected via something like NVLink or maybe Infinity Fabric. In the way that you've implemented this, can I model those kinds of interconnection networks?
Yeah, first, I will just be honest here. I don't know if that's interconnection networks works with APU. 1 second. Okay, I don't know if that's interconnection networks work with APU. But yeah, so I cannot answer that question right now.
Maybe let me help there. So the way that we've designed it thus far, like Bobby said, is is building on top of the the APU kind of support that exists right now. And so adding the kind of features that the questions are asking about here, that would require that you have something like a PCIe model that's fully functional, and that you have something like a discrete GPU support in theory that goes across and uses that kind of thing. So right now, the way we've designed it is where we're assuming one single unified address space, and so we don't have the kind of support that the questions are asking about. But I think as the support for PCIe and DGPU and that kind of stuff comes along, it would be somewhat straightforward to take the kind of support Bobby's added and apply it on top of those kind of things to get the kind of system you're asking about, if that helps.
Yeah, that makes a lot of sense. Let's see if there are any other questions. I'll ask one more, hopefully a quick question, which is, what kind of workloads are you using? How do you find multi-GPU workloads? This is something we're struggling with in our research too. So how do you find these multi-GPU workloads?
So yeah, so I run 4 workloads here. So simple multi-GPU, there is a simple multi-GPU program from CUDA that we hipified. And the other 3 workloads is basically initially for a single GPU, but then we do some input data partitionings to, so we modify the workload so that it could support multiple GPUs. And the way we modified it is that so that each GPUs will run the same kernels, but it will work on different portion of the data. So yeah, does that answer your question?
Yeah, that makes sense.
Yeah.
Maybe to paint a bigger picture there, Jason, other than the kind of frameworks like PyTorch and Cafe and stuff that kind of naturally do this, there isn't really a lot of benchmarks. And then Chai, I think, would be the one exception. But otherwise, there's not a lot of benchmark suites out there that provide the kind of support that you're asking. And so that's why we've spent the time, writing them ourselves to model this kind of stuff. But I do think that would be, an interesting addition to the community is coming up with a suite, maybe building off Chai to do something more complex, but that allows you to model those kind of things.
Yeah, that makes sense. So there's one other add-on question real fast. How much do these results that you see in the simulator match with actual multi-GPU configurations? Have you done any testing compared to hardware?
Okay, so that's a good question. So for now, we haven't compared it to real hardware just yet, but that's definitely in our plan. So we have like multi-GPUs getting ready to be installed in our labs. But then, yeah, it's got delayed a little bit because of the pandemic situations, but that's definitely in our plan. But for now, we haven't verified it and compared it with real systems.
Gotcha. Yeah, I know that's, but from experience, it's pretty expensive to set up one of those systems. So there's one more question on YouTube, which is there a plan to add a graphics pipeline? And I actually think we might want to defer that question to some of the other GPU talks later in the workshop. So thank you for that question. I will try to remember to come back to it. Remind me if I don't. Okay, great. Thank you.
Thank you.
So let's see, the next talk, I should have grouped all these GPU talks together so it could just be in GPU mode here. So it looks like our next talk is the gem5 GUI support. So let me stop sharing. So I'm not sure which of the GUI people are going to present. Okay, great. So I guess I'll briefly introduce this group. So Ahmed, Ravi, Rohit, and Shabam are a group of undergrads here at UC Davis who have done an absolutely fabulous job of coming up with this tool as their senior design project. So I'll let them take it away.
Hi guys, like Jason said, we're a group of senior design students from UC Davis working on creating a GUI for GEM5 with the supervision of Jason and Bobby. We basically made the GUI out of basically just all Python in order for it to work with GEM5 pretty nicely. We used PySide as our UI framework, and we've been working on this for the past 5 months.
our main motivation for building this GUI was to provide an easy way for user interaction and to give a better user flow to the current process of using gem5. As I'm sure most of you know, to configure systems right now, you'd have to write long Python scripts. And so we wanted to move that whole process out into a more visual fashion.
So our goals were to be able to drag and drop sim objects into a model and connect the ports with wires, and then being able to modify the simulation object parameters in a sort of drop-down menu of the parameters, and then be able to configure and test different systems. Then we would want to be able to save different model files and access them later, similar to any sort of application. And then another important one was to be able to create simulation objects derived from existing objects, and being able to export a design to multiple file formats. And finally, so one thing we didn't get to was actually be able to visualize simulation results. And lastly, being able to run the simulations from the GUI via a one-click simulation button.
Sorry about that, I was muted. Our current functionalities are mostly kind of like the core. So like Rohit was saying, you can add objects, connect objects to each other with wires. You can set the parameters for each object and save UI model files. And then once you simulate with a one-click button, the config.json file is generated within the repo. And you can also use shortcut keys for, I guess, convenience stuff. I think that's the basic overview of what we have for the GUI right now.
Great, thanks. So let's see, as people are thinking about their questions, are there any limitations to what this GUI can do so far?
In terms of, yeah.
Can you talk some about what the limitations are?
I think one of the obvious things is like the UI interaction. If you ever try to spin it up, one of the first things that you'll see is drawing ports is kind of like all over the place. It's hard to explain, like just talking about it. But one of our goals was to make things as clear as possible, and sometimes the wire drawing doesn't make it look as nice for usability anyway. I guess relating to gem5, Ravi, would you know, I guess, what we're still missing?
In terms of gem5, it should work. Say if you have the correct system on built in the GUI and there aren't any UI flubs and whatnot, it should work if you press instantiate. We've only tested it on not in models that like we can understand. Basically, we haven't tested it on like very complex models that are beyond the scope of our like own understanding.
Yeah, so let's see, Vipin asks, does the GUI support coherence modeling? I'll actually grab this one from you all so you don't have to try to figure out what's going on here. As far as I know, there's no reason why the GUI can't support Ruby, and it actually might simplify some of the problems that they were talking about with trying to connect up all the ports, since the coherence stuff is all within the Ruby object. So probably. So let's see, Tony asks, is the GUI capable of alerting a user to an invalid configuration?
Yes, so I think we have a level of error checking. I don't know if this is sufficient, but for example, if you have an attribute that you haven't set, it won't let you instantiate until you've set that attribute. So it'll actually show up in the GUI, like your object will be red, for example, or like an attribute that you need to define will be red. So you have to actually go out and fill it. Yeah, like if you look at this diagram here, anytime you click one of those objects, to the bottom left, it'll populate those attributes and you can modify it from there.
Great. And Tony also asked, how does the creation of new sim objects via the GUI work?
Okay, we'll talk like very briefly about architecture. The way that we've kind of set up our architecture is that every SIM object is connected to what we call like a UI sim object, was a SYM object. Very clever. Essentially, anytime you instantiate the UI representation, the SIM object representation gets constructed at the same time. And when you press, I guess, our instantiate button, what it does is that it'll go back and connect everything up. So it'll go from the root recursively down to all of its sub-children.
Let's see, Giacomo asks, when you visually generate the system through the GUI, is it possible to check at real time the generated Python representation? This is a great question and a great idea.
We were looking into that at one point, but other stuff came in the way and we decided to move on to just creating the config files as our first and foremost thing. We had a thing where we would produce the Python, but it took a long time. So it's definitely something we could look into, or this project can look into in the future.
There's definitely, since we can generate Python from this, I don't know if we could do it real time, but it's definitely possible to do something like that. Okay, let's see. Isaac and Puya both ask, can you import the INI or JSON files from non-GUI executions into the GUI and make changes?
That would be nice, but there's a lot of the thing about, I guess, our UI files is that they include stuff like position and like the objects and how they're, where they are and how big they are. Like that's important stuff. That would be nice though. It's just something we didn't think about because saving to a specific file format is an interesting problem.
Yeah, and I guess I'll quickly follow up and say, since they can load Python files, I don't see why we couldn't use the C++ INI hooks in gem5 to be able to do something similar there. So that might be possible. And the last question here is, I'm going to skip Juhuno's question, sorry, and go on to Brad's, which is, have you considered integrating prior work that attempted to visualize the debug trace output, such as the ARM03 CPU pipeline viewer?
So we do have a debug button over here at the toolbar, as you see, which brings up a window of basic flags you can set. I don't know if, so you can do a debug trace output, I'm pretty sure. We have a list of flags that are like Ahmed said, generated from the backend from gem5 into the debug window. So any up-to-date debug flag in the current version of gem5 should be on there, and you can click on it to enact the same trace output if you were to run the instantiation. I don't know if that specific one is in there, but
yeah, great, thank you. Thank you very much for your work, and thanks for the presentation.
Thank you.
Thank you.
Thanks.
Okay, so next we have towards full system discrete GPU simulation and the AMD Gem5 GPU simulator. So Matt and Tony are both going to be talking briefly here. I'm not sure how you all want to do this.
Hey, can you hear me, Jason?
Yeah, we can hear you, Tony.
Okay, I guess I have some slides. I don't see Matt on, so I can just go ahead and go through my portion of the talk, which is the Gem5 GPU model. So let me just bring that up. Okay. Hopefully y'all can see that.
Not quite.
Oh, I didn't click share. Okay.
There you go.
Okay. All right. So yeah, we released our GPU model a few years ago under with a emulated OpenCL environment for doing GPU compute, and we also executed our intermediate language level ISA called HSail. So I'm going to talk about the updates that we've made in the public release, as well as some future enhancements. So this is the high-level architecture that we support in Gem5 for the GPU model. So this is the high-level GPU core, what we call compute units. So at a high level, it's a 5-stage pipeline where we do fetching, dependency checking, wavefront scheduling, and then the backend provides all the execution blocks and memory pipelines. Our GPUs have vector register files, scalar register files. So in reality, it's a mix of SIMD and scalar instructions all within the same sort of warp, I guess what you would call it in NVIDIA terminology, but we call them wavefronts. So to that end here, the programming model that we support for compute is HSA, the Heterogeneous System Architecture Abstraction. So it's a standards body that provides APIs and queuing and different standards for heterogeneous systems in general, but they're really well defined for the GPU model. So when you think about a GPU core being a massively threaded machine, we sort of map that to what is called a wavefront or a warp. And then a higher level abstraction groups wavefronts together into work groups, which is like a single unit that can be launched to a single compute unit. And then overall, when we combine these in different dimensions, you can have what's called a grid, which encapsulates all the work items inside of your whole kernel. So CUDA calls these grids, thread blocks, and warps. And then at the very lowest level, what you think of as a single SIMD lane in a vector ALU is a work item or simply a thread. We don't really like to use that terminology, so I think of more of a wavefront as like a thread, because a single wavefront shares a PC, executes all the instructions in lockstep, and within a single wavefront you can have vector or scalar instructions. So for that reason, and just for other programming model reasons, we like to think of the wavefront as the actual thread. But it's perfectly fine to think of a single lane as a thread too, if you want to do that. Because the GPU is so highly software co-designed, it could be tied to like an OpenCL environment or other environments like CUDA, but we support ROCm. So this is the Radeon Open Compute platform. This is our HPC and hyperscale computing software ecosystem for GPUs. It consists of this stack that you see on the slide here. So we have a Clang LLVM compiler and then associated compiler libraries. We have a runtime that's called Rocker, the Rock runtime. And then there's two drivers. One is a user space driver called the RockT, RockThunk, and then there's the RockK, the kernel driver. And so we support the off-the-shelf versions of these libraries. So we're no longer emulating our software environment, except for the user space the kernel level mode driver, which we emulate. But that's something that I think Matt's talk addresses. So moving towards full system and including the full stack. The main parts that we interface with in the hardware that sort of implements the interface is the command processor. So it knows how to interpret packets and driver commands from this stack. So we want to make this as extensible as possible. So it's pretty easy to move to different environments, which requires you updating sort of the interfaces in the command processor and other things like that. We've added support for the GCN3 ISA, which is ISA about 2 generations ago, and we have some internal work that's added some newer ISAs, but the idea is that we just have this class of instructions where you can have vector memory, scalar ALU, or vector ALU, and then also the data store, which is our scratchpad memory. And so they're broken down into groups nicely, and we made sure to follow Gem5's convention where we hid all the details behind some generic instruction API So we have the instruction API that the core models use to interact with the ISA state, and then the backend implements all the specific API functionality. And so this enables us to really extend it easily to other versions of our ISA, and it would be not too difficult to extend to even other ISAs, not from AMD as well. Yeah, so in summary, we've released this GPU model and we're working on pushing all the updates to support the machine ISA and the ROCm stack to the mainline repo. We're continuing working on new features and enhancements, bug fixes, and the nice thing about this model is that it's CPU GPU, so we can have a full heterogeneous system co-executing and synchronizing and things like that, which enables us to run the full stack easily as well. And the code is available on the Google source as usual. So thank you.
Great, thanks, Tony. So it doesn't look like Matt is with us still. I don't know, let's see, is Brad on? Brad, do you want to give a quick pitch for the full system GPU thing?
Hi, can you hear me?
Yep.
Okay, yeah. So I know Matt was sick yesterday, so he maybe is not able to make it, fortunately. So I think I have the slides, so I can go through a couple. How much time do I have, Jason? How much more time?
5 minutes. So
okay.
I mean, you could do like a 2-minute pitch and then leave some time for questions. I think that would be best.
Okay. Yeah. So how about I just show up a couple pictures from this slide deck, if I can.
Okay, go ahead. And feel free to start asking questions, everybody. What we can kind of start pegging Tony with them.
Okay, are you able to see that?
Yep.
Okay. Yeah, so as Tony basically already summarized, we've have SE mode simulation for GPUs out there. It's been on a staging branch for a while, and as Tony mentioned, we're working hard to get all that checked into the main line here very soon. And that's effectively that picture on the left here, where we have the emulated system calls, and we have an emulated driver of the ROC-K. But it's been very difficult to kind of stay up with the ROCm stack as it constantly evolves. People know that GPU compute is a very evolving field on the software side. So to avoid us having to continually update our emulation of our driver and deal with a lot of software complexity within gem5, we're effectively going to go the complete full system mode, use the off-the-shelf GPU kernel driver, and run that all directly on the simulator. And yeah, I'm not going to go into all these details again. Matt's full talk is on the website, but I think one of the things I do want to point out here is I believe this is the first device model. Is that showing up? Sorry, I'm going to make sure this is not on there. Yeah, this is the first PCIe device model I believe it's added to gem5. And so, as part of this, we're adding a lot of support for not only PCIe extensions, but also sorry, I guess I was hoping there was a better picture, but for distinct separate address space for the device. And so, if you're following the patches online, specifically one that was just posted by Matt a few days ago, you see us getting the support into the main line. So yeah, again, there's a lot of details to get into later, but I did want to point out that we're trying to be as open as possible with our development here. The great thing about AMD's software stack is completely open source, including the driver, and therefore, there's really no reason for us not to completely convey where we are in terms of adding these particular details needed and features needed to run the full GPU software stack. And so you can, again, go on all these links on Jira and track our progress. Okay, with that, I'll stop there. And again, I apologize for the somewhat chaotic presentation here. But hopefully you got the big picture, and we'll take questions now.
Yeah, no worries. If I learned anything from teaching this quarter, it's that everyone has to be very flexible in these times. So we are happy to be flexible. Let's see if we have a couple questions here. So one of the questions, and I think why don't Tony's kind of answering in line, but Brad or Tony, why don't you answer this generally? What is the plan for APU support versus discrete GPU support?
So the question is what's our roadmap for APU support versus DGPU support?
I mean, there's been multiple questions about this, so I was trying to kind of combine them all together and just let you talk about, what models are going to support the DGPU, what models are going to support the integrated GPUs, what does ROCm do, that kind of stuff.
Yeah, so I think it really comes down to ROCm support. So people who've been following the ROCm stack, again, it's all open source, and you can follow it on GitHub. For the last couple of years, ROCm has primarily supported our DGPUs, and therefore that's why we've shifted our simulation support to support DGPUs. So going forward, assuming that stays true, and unfortunately I can't divulge anything more than that. We're going to primarily support DGPUs going forward because, again, that's where the latest ROCm support is at. The APU support, dates back to that 1.6 version, and I believe it hasn't been officially supported since then.
Okay, let's see if there is another specific question. So Haji asks, are there any benchmarks available in this intermediate language? I'm not sure exactly I know what intermediate language he's asking about.
Yeah, is that a question about the prior HSAIL intermediate language? Yeah, so Tony was lead author of a paper a couple of years ago about that.
I don't think they're asking about any benchmarks in the IL. I think maybe they were thinking I was talking about GCN3 as like a new IL or ISA. But yeah, I know we have lots of workloads, so you can the model's capable of running several complicated advanced workloads. We unfortunately can't release them, but I know Matt Sinclair and his student Kyle are actively working, and I believe Kyle has a talk in this workshop about the workloads they're releasing. So definitely lots of interesting workloads.
Great. So I have one more quick question. We're running a little bit late on time, but I kind of, since I have you on the spot here, I'm going to ask it. So a few years ago, you released the HSAIL GPU. It looks like we're kind of updating and dropping HSAIL and now using GCN3. In a year or two from now, are we going to drop GCN3 and move to GCN4 or whatever's next? Or is there some idea of a continuity or ways to make incremental changes to these ISAs?
No, we definitely, I don't see any reason to deprecate them. We already are supporting the Vega ISA, which is, the current state of the art for HPC GPUs that we have. So, and that is seamless. Like I said, we designed the ISA interface to be very generic. So all we had to do was, I mean, it was easy because the ISA hasn't changed that much, but still, as long as you can implement the ISA with the API we have now or slight modifications, and it should be completely easy to have these all coexisting side by side, just like with the CPU ISAs.
Yeah, and if you don't mind, can I add just a couple of things here? So I do want to point out that AMD is very much invested in publishing our machine ISA, unlike other GPU vendors. And you see that continually, even with our latest RDNA ISA also being completely open spec. And I foresee that continuing in the future for us. And then also, do point out that there is performance loss by going to an intermediate IL. And so the reason why we've shifted is, for the additional opportunity for compilers to directly target the end ISA. So that's a direction that AMD has made in general in the the compiler strategy. It's not something specific to our simulator at all.
Okay, great. Well, thank you very much. Let's switch back over here. So now we have a talk from Nils about a modular and secure system architecture for IoT.
Yeah, so let me share my screen. Can you hear me?
We can hear you fine.
Good. So, no.
And we can see your screen now.
Yeah. Okay. So yeah, hi everyone. I'm Niels from the Barkhausen Institute in Dresden, and at the Barkhausen Institute we are working on a modular and secure system architecture for the Internet of Things. And yeah, let me give you a quick motivation. So we have complexity nowadays on both the hardware and the software side. So on the software side, we have huge and monolithic operating systems that are also vulnerable for that reason. And of course, we want to depend on them on basically all kinds of devices that we have in our daily life. On the hardware side, we also have a lot of complexity nowadays. So we have, for example, heterogeneity with different accelerators and specialized components that we integrate. We also have untrusted hardware components, like if we want to integrate components from third-party vendors, like a modem, for example. And last but not least, we have these side channel issues nowadays. So we have a bit of similar problems on both the hardware and the software side. And for the for operating systems, the microkernel-based systems have been proposed as a solution quite some time ago already, and they have proven that this is a valid solution for very security critical systems that we are focusing on here. So the idea is that we basically use the same approach for both hardware and software components here. And yeah, we built this M3 system architecture here. That's the name. And the idea is that we have a bunch of different processing elements here integrated into a network on chip, like general purpose cores, accelerators, and so on. And one of the key ideas in this architecture is that we add a new hardware component next to them, which is the Trusted Communication Unit, the TCU, which at first gives these potentially very heterogeneous processing elements a uniform interface that allows us to forget about the differences for a while now. And it's a communication device, so you can establish communication channels between these tiles or between the TCUs in the tiles. But they are isolated by default. So by default, you cannot do anything. And this is also why we can integrate untrusted components and isolate them from the rest of the system. In terms of the operating system, the idea is that the kernel is running on a dedicated kernel tile, and the applications are running on the remaining on the user tiles here. And the kernel is then remotely controlling the user tiles and is mostly responsible for establishing communication channels between the user tiles. Yeah, we simulate the system in gem5, so we have added a model for the TCU to gem5, which was relatively straightforward because of the flexibility of gem5. Yeah, we also are working on a hardware implementation, so we have a hardware team at the Barkhausen Institute, and there we use RISC-V for the hardware implementation, which is also why we added full system support for RISC-V to gem5 recently. Yeah, and with that, I'm ready for questions.
Great, thank you. So as people are thinking about questions, I'll kick it off. So I want to say that this is really, really cool work. It's my personal vision for gem5 to be used for these kinds of studies, and so I'm really excited to see that you're doing it. So with that, can you talk a little bit about why you chose to use gem5 and not some other kind of simulation or emulation methodology?
Yeah, so on the one hand, we of course need the accuracy. So we want to have real performance data and accurate performance values. And therefore something like QIMO or Box or some other simulators that are out there is not really an option. And also the flexibility or modularity of gem5 really helps for us so that we can add a new component and flexibly combine things together, like having multiple system objects as we do that and having a crossbar between them and all these kind of things. So that really helped. And I think these are the main reasons for that.
Cool. So let's see, Matt Sinclair asks, this is really cool. He agrees with me. For IoT type devices like this, OS jitter tends to be an important artifact. Since gem5 does not have real-time operating system support, how do you take this into account or add the appropriate support to get around this?
So we are not looking too much into real-time issues at the moment. So I think the plan for later is that we have a kind of real-time tile where we have a specialized operating system that is taking real-time guarantees into account. And that is then isolated in this tile, and that doesn't influence the other tiles so much. So that's the plan, but we haven't looked into that so far.
Cool. Let's see. So as other people are asking questions, so one of the things you mentioned in your talk was that you're both doing evaluation on gem5 and on an FPGA. So could you talk a little bit about the trade-offs there between getting this up and running on an FPGA versus using gem5?
So we just started with the FPGA, so we don't have that much experience yet. But of course, it's a lot more effort to develop that to have a real hardware implementation of the TCU, which is the main thing that we need to develop for that. But of course, we can have bigger simulations with that because it's faster than gem5, and we also of course want to have a real hardware implementation to see how large things are and how costly they are, and also to make our gem5 model more accurate. So this is also some goal that we have with that.
Cool, great. So let's see, I think Andres was not asking a question, but answering Matt's question there, saying that in principle, we could get a real-time operating system to work on gem5, but probably haven't done it yet. Let's see if I had any other questions here. Oh yeah, okay, so Ayaz has a question, which is, did you have to add the support for any secure operations at the ISA level since you were looking at security?
No, we didn't. So actually, we want to reuse the processing elements like a core, for example, as they are. Also because we want to have heterogeneous systems in the end. And therefore, we didn't add anything there. So the additions that we make is really just the TCU, which has the security operations that we need.
Cool, thank you. So Rashiva asked, is the RISC-V full system available with upstream gem5?
Yes, that's available now.
Yeah, cool. And thank you very much for that effort there.
You're welcome.
Okay, cool. Thank you very much, Nils. This was a really interesting work that you have here.
Yeah, thank you.
Okay, so next up, we have two more talks. So Matt Sinclair is going to talk about modeling modern GPU applications in gem5, which is our last GPU talk of the day.
So Nils, okay, never mind. I was going to say, I need to wait for you to release the sharing before I can.
Unfortunately, there's no way to atomically switch the sharing.
Right. Anyways, hopefully everyone can hear and see me now, and the slides as well.
Let's see. Yes, we can.
Okay. So yeah, thanks, Jason, for the introduction. I'm Matt, and as he said, I'm going to talk about the work Kyle and I have been doing, which you've heard maybe a couple of times throughout the the workshop, on trying to get the support for the GCN3 GPU that Matt and Brad and Tony and others have been telling you about, more usable and easier for people to adopt in the wider community. And just to give you a quick background, as many of you know, GPU applications have become increasingly prevalent, and the latest sort of next generation workloads are things like DNNs and RNNs and AR and VR. Now, in this talk, I'm going to focus mostly on the high level support, especially for machine learning. But just to answer the other question that came up earlier, we are working on VR and AR support as well. But the issue both that I faced when I was working with Brad and Tony and others at AMD directly, and subsequently that Kyle and I have been trying to tackle in academia, is that getting this GPU model up and running is very difficult, even for people who have a lot of expertise. I think Tony was pretty polite there when he was talking about the effort to get it all working. And part of the problem here is that the software stack, especially the software stack for machine learning, is not built for simulation. And so I'm going to just quickly summarize this because I think Tony and Brad did a good job of talking about it already. But the model that we're focusing on in this work is that APU that Brad and Tony mentioned, where you can model CPUs and GCN3 GPUs. And in the work that Tony led, what it allowed you to do is it allowed you to run a unmodified ROCm user stack, and specifically it meant that you could run HIP and HCC or HC applications. And in subsequent work that John Alsop and myself and others at AMD did, we added support to run machine learning, or as AMD refers to it, machine intelligence or MI applications. And again, like you heard before, right now, all of this is modeling in APU and done in SE mode, of course, although that is moving towards discrete GPUs moving forward. But the challenges to get this running, as you heard a little bit from Brad before, is that you need a specific version of software. Specifically, you need ROCm 1.6. And if you want to run things like machine intelligence workloads, you need specific versions of all the different software that layers on top of the picture you see here. For example, the MIOpen and the MIOpen gem libraries, you need the versions that are compatible with ROCm 1.6. And in practice, what I found both when I was trying to get this all working originally, and I know a lot of you have found based on the number of posts on the gem5 forum, even just in the last year, about trying to get this all working, is that it's really hard to get all these libraries and all these pieces. Jason, just so you know, it says the recording stopped, but I'm going to keep going. So what this ultimately means is that it's challenging to install and get everything working correctly. And so the goal that Kyle and I had in this work is to find a way to make it easy for new users, perhaps some of you, I know a few of you at least, to pick up this Gem5 GPU model and get it up and running with the kind of things you care about without spending a lot of time fighting getting all the software you need working correctly. And so the solution we took essentially has three pieces. So first, what we did is we designed a Docker, and what this does is it creates a known working environment. And so this essentially eliminates all of the setup time that many of you, and myself included, had struggled with in the past, and makes it really easy to reproduce and add, whatever applications or widgets that you want to the simulator. And as Tony mentioned before, we've now validated this on the public version of Gem5, so not the AMD internal model, but we've validated that it works on a number of GPU applications, both those without machine intelligence and those that are using the native machine intelligence libraries. Second, because the software stack was not explicitly designed to run on these kinds of in simulators, we ended up making a number of optimizations, which are in the longer version of the talk that Kyle gave. But essentially what they boil down to is finding ways to avoid simulating things that are not part of the application's region of interest. So for example, what machine learning and machine intelligence libraries do is the first time you run a kernel, they're going to try and every possible option. So gems and FFTs and maybe Winograd or direct, other kinds of ways of doing a gem kernel. And they're going to run all of them and figure out which one is fastest. And then from then on say, oh, okay, I'll just run the fastest one. On a real piece of hardware that's reasonable, in the simulator, that ends up quadrupling or quintupling, or maybe even worse in some cases, the amount of simulation time it takes. So we've came up with ways to avoid doing that. And finally, what Kyle is currently in the process of is integrating his Docker and the tests that go with it into the GPU regression on the develop branch. And the goal with this is to ensure that all of the future changes to the GPU model are tested and validated, and we can make sure that we're not breaking support as we go. And so if you're interested in this, you want to use it, or you just want to understand a little bit more how to use it in general, the blog post as well as Kyle's longer talk includes a demo of how to use it, how to get it up and running. And our hope ultimately is that this will reduce the barriers to entry for simulation and make it easy for many of you, those of you who are interested in doing CPU, GPU simulation, to adopt this and add all those cool widgets that you were asking Tony about a couple minutes ago. So with that, I'm happy to take any kinds of questions. I know on YouTube and as well as in the chat that people had posted some questions previously, which I tried to answer, but I'm happy to revisit them now or answer new ones that have come up.
Great, thank you, Matt. So this may or may not be a question you can ask, but Dan is asking, is gem5 going to move away from APU models in favor of DGPU?
You know, I think Tony and Brad answered that previously, and I'm not sure if they want to chime in again. Ultimately, I'll give my opinion, and then Brad can give you maybe the company line. I think, as Brad said before, the ROCm stack is moving towards supporting DGPU heavily and APU less heavily. And so what that means is we have a model right now that includes APU support and does not include DGPU support. In the future, it's going to depend, I guess, on where AMD decides to put their support, but it is not impossible to make sure both are supported. It just would require some effort to keeping all of the syscalls and everything in SE mode that are currently working modeled in the newer versions. And I know not from personal experience, but from seeing Tony and Brandon Potter and Matt Paremba and others go through that effort, that it is quite a lot of work. So I don't want to mislead people and make them think that it's implausible, but it certainly could be done. In terms of what I think should happen, certainly I think having support for both of them is important. And you heard Bobby talk earlier about the kind of work we're doing both with coherence protocols as well as multi-GPU support to address some of those kind of things.
Great,
so
thanks.
Brad, I don't know if you want to chime in with the company line or the company view here.
I think that's probably a pretty good thing, especially since you're outside the company. I think that's probably the right way to answer it. All right, so one more quick question, and this will be the last question here. For the MI type workloads, the machine intelligence workloads, can you speak to the kind of runtimes we should expect for simulation time?
Sure. I mean, just like any workload, the bigger input sizes you use, or the bigger, the more layers, say, that your machine learning workload has, the longer it's going to run. So I can give you some examples specifically from DeepBench. So DeepBench, if you're not familiar, was released by Baidu. And they have convolutions and RNNs and gems primarily in that suite. And so if you run a really small RNN, and by small, just to give you an idea, I mean small as it relates to like batch size and hidden layer size, what that will run you is it'll be maybe an hour or two of runtime. If you crank up the batch size or the hidden layer size, say to like hidden layer size of 512 and batch size of 32 or 64, you're going to be looking at maybe a day of simulation after the optimizations that Kyle and I put in. So there is a cost certainly to modeling in the level of detail that gem5 and the GPU model in specific has, but the goal or maybe the feature, if you will, of the optimizations Kyle and I have been doing is to get rid of as much of the stuff that takes a long time to simulate but doesn't give you a lot of return on investment or bang for your buck, to make sure that as much of that is being done on the real CPU as possible. And in the long run, I think integrating with KVM and these other kinds of supports that hopefully can be extended to GPUs will be another way to keep extending that and making it easier to only simulate the parts of the applications you care about. But maybe one last quick point to put in there. I know this is a long answer, but keep in mind that right now the kinds of applications that Kyle and I have been running, and I'm pretty sure that the AMD folks have been running internally too, what they do is what we call native machine learning libraries. And what that means is if you were using MIOpen, which is AMD's equivalent of cuDNN, if you made a call directly to that kind of library, it will then work. If you want to use something like PyTorch or TensorFlow or Caffe, those actually aren't what I would call non-native applications because they go through these frameworks and make those calls. And right now we don't have those working. There's only what I would say is partial support for them. But if you run those, I would expect the overheads are going to continue to be higher than these, especially until something like KVM support is added. And I think that's why the full system work that you heard about before is really important, because it'll help us sidestep as much of those problems as possible.
Okay, great. Thank you, Matt. Thanks for that talk and answering those questions. Okay, so in the last few minutes, I'm going to turn this over to Tiago to talk about implementation of a flexible cache coherency protocol for the Ruby memory system, which I have to admit is, I'm sad that it's last because I'm most excited about this work.
All right, can you guys hear me and see me?
Yes.
Okay. How do I share my screen?
Should be a big green button down at the bottom middle. And then one extra button push after that.
Just a second. Okay. You should be able to see it now.
Yep, we can see it. Thank you.
Okay, so my name is Tiago. I'm with ARM Research, and I'm gonna highlight our work on implementing a flexible cache coherency protocol for the Ruby memory system. Okay, so as you may know, Gem5 has two memory systems, Classic and Ruby. Classic is very flexible, very easy to set up, but it has some drawbacks. One of them is some simplifications you have on the cache coherence side and some limitations on the interconnect that make it not a very good choice for modeling large SoCs like systems with 64 cores or more. On the other hand, you have Ruby, which models all those aspects in detail. You have very detailed interconnect models, very detailed cache coherence protocols, but it's not as flexible as Classic. For example, each protocol has its own cache hierarchy, and you cannot change that without changing the protocol, and that's not very easy to do if you have worked with Ruby before. So this is the thing that we want to address with this work. We want to have a Ruby protocol that allows you to set up arbitrary cache topologies, just like you can do in Classic. To put it into Ruby terms, instead of having a protocol that has a state machine defined for every cache level, we want to have a single state machine implementation that you can instantiate and configure at any level of the cache hierarchy. So you can use the same state machine to have a MESI protocol with 2 levels of cache or 3 levels of cache, or a combination of MESI with a MoESI less level cache. So the first step to do that is to define a flexible set of protocol level transactions that we can use to model all these configurations. And for that, we looked into ARM's AMBA5 CHI specification. So CHI stands for Coherent Hub Interface, and is the communication interface that is used on current ARM SoCs for interconnect and cache coherency. And CHI provides a set of transactions that we can use to model multiple instances of MESI and MoESI cache coherency. So if you want to know more, you can look at our blog post that has a link to the CHI specification, and you can also look at our workshop video that has some examples of some CHI transactions. So in the end, we end up with a protocol that has 2 state machines only, one for the memory controller, which represents a CHI slave node and will interface with the main memory, and the cache controller, which we can configure to be a top level cache or intermediate level cache like a private L2 or a shared L2, or it can be configured to be the system home node, which is the point of coherency that also includes the last level cache. And the same controller can also you can also completely disable the caches on the same controller and use it as a DMA request node, or as home node without a cache as well. And on the right side of the screen, you have just a snapshot of the state machine definition for the cache controller that has some of the options that we are targeting in the final implementation. Just to give you an example, so this is the kind of things we want to be able to configure. For example, inclusivity of data, if you want to have a inclusive cache, a non-inclusive cache, or exclusive cache, and we want to be able to define this separately for shared or for unique or exclusive data. Also ways to disable the shared dirty state, which is basically the owner state of Moesi. So you can switch between Moesi or Mazi modes of operation, and also some other options to enable or disable optimizations that you have in the CHI specification, like direct transfers between request nodes, direct transfers between the main memory and request nodes, so you can tweak the protocol with the behavior that you want to model. Yeah, so this is in a nutshell the work we are doing. Of course, we plan to upstream this soon, so everyone can use the protocol. And as plans for the future go, we want to keep extending this to support things that we currently don't have in Ruby, like support for all the prefetchers we have in Classic, and also support for cache maintenance operations. So that's it. I'm open for questions now.
Great, thank you, Tiago. So we're running a little bit short on time. I wanted to try to end by 2 hours, so we'll take just one question.
Okay.
Oh, crap, we have 2. 3. Oh man, people can get their questions in real fast since I said only one question. So we'll take a couple. Let's start with from Adarsh, which is similar questions to what I had. Do you have any plans to support to verify the protocols? And I think testing is kind of the question that I had as well.
So basically how we are testing this. So basically what I have is a draft generator that generates multiple patterns with lines that with false sharing, true sharing, multiple cache sizes, and it's we basically generate a few thousand test cases, and once all those once we are able to execute all those test cases without deadlocking and without getting any wrong results, I'm happy with the I'm assuming it's mostly working, but we don't have any methodology for formally verifying the protocol.
Gotcha. Yeah. Okay, so we'll do one more. Sorry, I'm going to go with the first person who got it in, which is Victor. And his question is, are you going to implement all AMBA 5 chai specs like unique dirty partial state or retry ACK?
No, we are going to support a subset of the transactions. Right now, there is no plans to have partial cache lines, but we are going to have retries, and we're not going to have no partial cache lines. So I mean, the spec covers a pretty big set of features. I mean, you can ask me offline if some specific feature will be covered, but partial cache lines is not going to be one of them.
Great, thank you. And so since we're a little bit over, I'm sorry that we're not going to be able to get to all these questions. You can take it offline with Tiago or post on the Gem5 development list, because I think this is coming soon, and I think there's going to be quite a bit of conversation around it when it does come. This is an exciting new feature, and I'm looking forward to seeing it. Thank you.
All right, thank you.
Okay, so briefly, just to wrap up, and this will be very brief. So thank you very much for joining us at this workshop. This went at least as well as my expectations, if not extremely exceeding them. And so the last thing I want to leave you with is just remember that tomorrow we're going to have a town hall where we can continue some of these conversations. And I hope to see you there. Talk to you soon. Thank you for joining us.